Hello everyone. I want to continue our discussion by now introducing and discussing Chapter 9. I do not intend to include Chapter 9 in your exam, but it will be on your final exam, so this is still going to be pertinent information for you. So the topics, by the way, that we will cover in Chapter 9, we're going to skip this stuff here that's listed. But we are going to talk about the Newtonian picture of gravity, universal law, inverse square distances, the sensation of weightlessness, and ocean tides. Okay, so I want to start by this idea that Newton had that basically underpins this idea of the universal law of gravity. He was able to conclude that gravity was a force which was consistent throughout nature. And legend has it that, you probably heard the story of the apple hit Newton on the head and he suddenly came up with this idea. Um, it, it didn't happen quite like that, but there is some truth to the story. The story, if you want a more factual or probable version of it, actually is pretty relevant to us right now because Newton was forced to leave Cambridge University. University was shut because of the bubonic plague, just the same way our university is currently shut, and we're discussing these things virtually. Anyway, Newton didn't have the internet, and so he went to his childhood home during this time where the university was closed, and there was an apple orchard as part of the farmland that was near there. And the idea that he came up with about gravity was said to be inspired by noticing a falling apple and also seeing the moon sort of in the same time. He could see that, well, gee, the moon is being pulled around the earth. And the apple is also being pulled to the earth, and he made the leap to conclude that these two things really were the same thing, and that gravity, in that sense, was what he would call universal. So, the universal law of gravity, to put a finer point on it, specifies that everything that's massive is going to attract everything else that is also massive. And that force of attraction, if we want to quantify it, has to do with the product of the two objects' masses. And it's also inversely proportional to the square of the distance between them. So in mathematical form, you have this equation here that the force of gravity is going to be proportional to the product of the two objects' masses, inversely proportional to the distance squared between them, and this constant of proportionality is then known as the universal gravitational constant. We know now that it has this value, 6.67 times 10 to the 11 Newton meters squared per kilogram squared. And this is actually indicative of the fact that that gravity is actually the weakest of the fundamental forces of nature. This value, by the way, that I've just stated, had to be found experimentally, and the famous experiment which helped reveal that value was the Cavendish experiment. Previous attempts to find what the value of capital G, by the way, don't get capital G mixed up with little g, and we'll talk about those two together in a second. Anyway, the way in which you need to experimentally determine this capital G was technically very difficult to achieve. And so although some attempts had been made, it wasn't until more than 100 years later, after Newton developed this law of universal law of gravity, that the Cavendish experiment was performed at Cambridge and was able to then measure the value of G. So here's a picture of the experiment. How it worked was essentially that you had two massive objects, And through a torsion scale, you were able, the details of that we're not going to go into, but essentially you're able to measure what the force of attraction is between these two massive objects or spheres. So if you remember when we were talking about Newton's second law, we said that force equals mass times acceleration. So that's essentially mg in this case, where this is little g, not to be again confused with big G. But if that's the force of gravity and this is also the force of gravity, then we can equate them to each other. So essentially this mg, we'll pick one of these two things, m1g, should then equal capital G m1 m2 over the distance squared. Okay, and then you'll notice these things cancel. And you can then solve for this capital G. And so by measuring this force, you can basically figure out what this capital G is, because you know these other things. You know the masses involved, you know the distances between them. So once you have capital G, you can apply this same reasoning here to the Earth itself. It was already known what the radius of the Earth was, okay? And so we can set this force of gravity equal to this force of gravity, and the distance between, say, you and the center of the Earth is effectively the radius of the Earth. So that's going to be your d for your distance squared. And then, since you already know what the acceleration rate of gravity is, right, this is your 9.8 meters per second squared that we've discussed before. Okay, then the only thing you don't know, you've calculated g already through the Cavendish experiment, you know the acceleration rate of gravity, you know the radius of the Earth, so all that's left to find then is the mass of the Earth, and this is how the mass of the Earth was then ultimately determined. So I would challenge you to try and figure out that computation on your own and see if you can come up with the correct value. Do it on your own, and then it's easily Googleable to find out what the mass of the Earth is, and you can compare and make sure you've gotten the right value. Okay, so gravity, like many other laws of nature, is what we would call an inverse square law. We said just a little bit ago that it depends inversely on the distance squared between the two objects. And we experienced this already when we discussed sound, and we talked about how loud the sound is that you might register at a certain location, and that had to do with 1 over the distance squared. And gravity is the same way. You take two objects and you place them twice as far apart, and suddenly the gravity will now only be 1/4 of what it was before. Take and place them 3 times as far apart, 3 squared is 9, it will only be 1/9 as strong of a force as you had before. And that's the same thing we talked about with sound, placing sound or light. These sort of things are also inverse square laws. So it's nothing unique to gravity. It follows the same sort of relationship we've discussed before. And so if you think about it in terms of, say, the Earth, if I have an apple on the surface of the Earth that weighs 1 Newton, and I place it at a distance 2d, so this is where d is the radius of the Earth. Okay, so if I now place it at 2 Earth radii from the center, now it will only be 1/4 of a Newton, right? And then if I place it at, say, 4d, 4 radii of the Earth, it will only be 1/16 of a Newton. All right, so the upshot of this figure, though, is to notice a couple things. One, the force of gravity, like other such inverse square laws, it does drop off rapidly with distance, but also notice that it takes a while before you start to drop down to zero, and you're never going to actually achieve zero, right? Strictly speaking, I would have to plug in infinity here in order to get a zero. You'd have to be infinitely far away from the Earth. But we can get to a point where it drops off a lot. However, most of the astronauts, say, that are in orbit, low Earth orbit, are nowhere near that distance from the Earth. So why is it that they talk about astronauts experiencing what we would call weightlessness? Well, weightlessness is really just the lack of a support force on your body, or the lack of a normal force on your body, the same way as what would happen if you were in free fall, which is why a lot of times when they are training astronauts, they take them up into a jet and they just nosedive to put them in a situation of free fall. So that you get some of that weightlessness sensation. Of course, always the force of gravity is still acting on the astronaut. It's not as though there is no longer a force of gravity acting on the astronaut. It's just that there's no support force pushing back up onto the astronaut to give them a sensation of weight. You've experienced this to a certain extent in your everyday life. If you get onto an elevator and you're just standing there, you feel like your normal weight. That's because the normal force, or the support force, is exactly balancing the force of gravity on your body, and these two things you experience to be the same, and you feel your actual weight. But once the elevator starts moving, in that initial moment where it's starting to accelerate, say up, then you sort of feel heavier, right? And you've probably all experienced this sensation when the elevator starts to move and accelerate upwards. That's because now you've got another kind of acceleration on your body. And if you think about what's happening in terms of a free body diagram, you've still got the same force of gravity on your body, which is equal to mg, and you've still got a normal force here. Okay, but through Newton's second law, when I sum these things, then what I'm going to find is that, we'll give this a minus sign since it's pointing down, plus n, I'm accelerating. This is no longer equal to zero. In the case where the elevator is at a rest, the acceleration rate, or even once it's moving at a steady velocity and it's no longer accelerating, that's why you only feel this at the beginning, then this right-hand side would be equal to zero. And so the scale that's going to tell us what the support force is on our body is reading this normal force here. And so if I solve for the normal force, I'm going to find that it's no longer just mg, it's mg plus this ma, which has to do with the acceleration rate of the elevator. Okay. In the case where you are descending in the elevator, it's a similar situation. The only difference is that when I set these two things equal to mass times acceleration, I'm going to have a minus sign here since I'm going down. And so then when I solve for the normal force, I will find, oops, this should say A. I will find that it is my weight minus this little force due to the acceleration of the elevator. And so in that moment, I'm going to feel like I weigh a little less than usual. And so you could then extend that to the scenario that, well, what if the whole elevator cable breaks? Well, now I'm going to be in free fall, and I will be just like the astronaut in outer space without a support force on my body, and I will experience that as if it's zero weight. Okay, so normally we would do these in class as clicker questions, so we'll just go through them together and you can kind of check your reasoning, pause if you want to, and think about what you would put if this were a clicker question. So in the example we just discussed, we were talking about different possibilities for an elevator moving. So if an elevator accelerates upward, what would the reading on the scale actually say compared to your normal weight? Okay, the answer to this question is that it would read a greater amount, So go back to that other cartoon in the previous slide and review as to why that is. And then the converse of that is if you're accelerating downward, the reading on the scale would say what? This time it will say less than what you would normally weigh. Okay, and if the elevator cable breaks and you're suddenly in free fall, then the normal force pushing up on your body is 0, so the scale is going to read 0. Okay, so it's important to remember though that if you were moving at a constant rate of speed, remember the elevator doesn't mean that when it's going up it magically whoops, I want to go the other way. It doesn't mean that that it's just the fact that it's going up that gives you this greater than normal weight sensation. It's that it's accelerating. Okay, which means that velocity is not constant. So that's why you're only experiencing this in the initial moment. Once it reaches a constant velocity, then you still have no acceleration, right? This would still be equal to 0. It's only the acceleration that gives you this sense of greater weight or less weight than usual. Okay, and then the final phenomenon we want to talk about when it comes to gravity is the ocean tides. If you've ever been to the shore, you may have noticed that at different times of the day, the level of the water is higher or lower. The reason for that is due to the fact that we have this moon and it's orbiting around us. And normally we're thinking about the force that we exert on the moon, but Newton's third law tells us that whenever there is a force on something, then there should be an equal and opposite force on the other object. And so it's true that we are exerting a force of gravity on the moon, but the moon is also exerting a force of gravity on us. And because there is one side of the Earth that's closer to the moon than the other side of the Earth, and this distance squared actually matters, as we've seen with the universal law of gravity, then the amount of the force on one side of the Earth is not the same as on the other side of the Earth. And so this results in some uneven forces which produce these bulges that you're seeing here. Now, the moon is not the only thing that's tugging on the Earth. Also, the sun is tugging on the Earth. And so when you have an alignment of the moon and the sun, either because the moon is in a full moon position where it's on the opposite side of the Earth from the sun and it's getting this full sunshine, or because it's in the new moon position, in which case it's on between us and the sun and the whole thing is in shadow from our perspective. At those 2 times of the month, which is approximately every 2 weeks, then the tides will be emphasized because the sun and the moon are working together to produce more of a bulge here by this different amount of force on both sides of the Earth. So during those times, the Earth is experiencing what we would call spring tides, which are more extreme tides than usual. In other phases of the moon, the tides will be less extreme than usual because the moon is pulling in one direction and the sun is pulling in another direction, and so these are perpendicular and they serve to somewhat cancel one another out, producing neap tides. There's still some tiding effect here, it's just not as great as usual. And so other phases of the moon will be sort of in between these things. Okay, and so that's really all I wanted to discuss about Chapter 9. I will go into Chapter 10 with you at some point next week, and I will be sending more information about your exam shortly. Thank you.